Okay, lesson 79. Most commonly pronounced as L'Hopital's rule, which is why I put the other spelling up here. You'll see both in the book, spelled La Hospital or L'Hopital. It's most commonly pronounced L'Hopital's rule. If you go up and say the La Hospital rule, someone's going to look at you like you don't know what you're talking about. Okay? Usually you hear L'Hopital's rule, based on the person. I don't remember what GFAM stands for, but as you can see, the last name. And Bernoulli made this rule to extend our knowledge of the limit as a quotient. So basically, we're looking at limits today that prior to today we would get stuck on. We could not solve them just by hand without looking at a graph. Today we're going to look at, okay, how can we solve these still by hand using L'Hopital's rule? So the idea behind L'Hopital's rule is that when you do the limit of a quotient, so the limit of a fraction, where the limit as x approaches a of f of x over g of x, when you get an indeterminate form. So an indeterminate form, sorry, tongue-tied, mean when you get something of the form 0 over 0 or infinity over infinity. Well, 0 over 0, it's not 0, but it's not undefined. It's just kind of one of those gray areas. And it's what we call an indeterminate form. Same thing with infinity divided by infinity. Normally, if you get 0 over a number or 0 over infinity, we can work with those things. Or infinity over a number, we can work with those things. We can't work with these. And so our rule is going to be, if we get an indeterminate form, then what we do is we take the derivative of the top, the derivative of the bottom, and then we try the limit again. Okay? It's a very easy rule to use. We can use it actually on some of the limits we've done in the past, where we've ended up looking at the graph or factoring or something like that. This will also apply. Okay, so I like this one. This is I don't know if I should use the word fun, but...
Fun, calculus.
Okay, but there are definitely some things that are not fun in calculus, right? And there are some things that are easier to understand. I feel like this falls into the easier to understand umbrella, okay? So I feel like this is a good place to be on a Friday 2-hour delay day.
Yay.
Okay, so example 1. You always want to start taking the limit as normal. You never jump just to L'Hopital's, because we have to make sure it warrants jumping to L'Hopital's and using L'Hopital's rule. So the limit as x approaches 0 of sine x over x. Typical limit, we take the value that we're approaching and we plug it in. So if you plug this in, you're going to be doing the sine of 0 over 0. What is the sine of 0? Sine of 0 is 0 over 0. We have officially hit an indeterminate form. Okay, so as I said, prior to today, we'd look at a graph maybe. If we could factor, we'd try some different techniques. Today, we're going to do something called L'Hopital's rule. And the idea of L'Hopital's rule is that, whoops, come on. Gosh. Okay, it's still going to be the limit as x approaches 0. But we're going to do, I'm trying to figure out how I want to write this out. We're going to do the derivative of the numerator. So I'm going to write this as d dx of sine x, and we're going to do the derivative of sine x with respect to x. And then on bottom, we're going to do the derivative of x with respect to x. I won't necessarily write it in that form every time, like once we get going and stuff, but for today's purposes, just trying to show you that, okay, that's what we're doing. Because we got that indeterminate form of 0 over 0, we're taking these derivatives. So, as you can guess, it is still the limit as x approaches 0. What is the derivative of sine x? cosine x over what is the derivative of x? 1. Well, I'm definitely not getting 0 over 0 this time, am I? So now we are ready to plug in 0. So when I plug in 0, I'm going to be doing cosine of 0 over 1. What is the cosine of 0? 1. And I think about my cosine graph, which starts up at 0, 1, doesn't it? So this is 1 over 1. And what is 1 over 1? 1. Okay, guys.
I used to hate limits, but
I like this limit rule.
Yeah.
There's certain limit problems I like. There's certain ones that are definitely a little more debatable. But I like L'Hopital's. I really do.
So all it is just if it doesn't work, you just take both sides.
Yeah. If you, it's not just that it doesn't work, but if you specifically get 0 over 0 or infinity over infinity. Yep. Take the derivatives, retry.
do it again.
Pretty much. Okay, shall we try example 2? And by the way, if you graph this, would the graph confirm this? Yes. But over half of your AP test, or at least half of it, is non-calculators. So you have to be able to process limits without looking at graphs a lot of time. And so that's why we have all these tricks and techniques. Okay, example 2. What should I do first?
Make sure that we get
Yeah. Don't just jump to L'Hopital's. And that's hard to say today because what am I teaching today? L'Hopital's. But try it. See what happens. So we're going to say the cosine of 0 minus 1 over 0 squared. What is the cosine of 0? 1 minus 1 over 0 squared. Which, of course, is 0 over 0. I know, shocker, right? It's hard to teach because it's like, okay, you're going to see the same thing over and over, but that's all right. So we're going to do the limit as x approaches 0, and I'm going to take the derivative of the top, so the derivative of cosine x minus 1 over the derivative of the denominator, so the derivative of x squared. And I'm just putting that ddx there so you can see what I mean. I will say, on an open-ended problem on calculus, on a free response, that's the word I want to use, there are certain ways you have to show that you're using L'Hopital's rule. And you have to show that it goes to an indeterminate form. So the fact that the limit of the top is 0, the limit of the bottom is 0. That's something you have to show for them to give you credit for using L'Hopital's rule. So, okay, so this is still the limit as x approaches 0. What is the derivative of cosine x minus 1? Negative sine of x over, what is the derivative of x squared? 2x. Now I'm going to plug in 0. What is the negative of sine of 0? Still 0. What is 2 times 0? 0. What just happened? We got an indeterminate form again. So yes.
So much more space.
Sorry. I should pre-warn, but yeah, there's a reason I made sure to squeeze that in, because if you run into an indeterminate form a second time, then
just keep doing it.
you reapply L'Hopital's rule again.
I was gonna say that's about as easy as doing the second derivative and all that.
Okay, so now it's the limit as x approaches 0. We're going to do the derivative of negative sine of x over the derivative of 2x. And we hope things work out better this time, right? So it's still the limit. Notice I keep writing that limit notation in every time so I don't forget to take the limit. Limit as x approaches 0. Derivative of negative sine of x. Negative cosine x. Derivative of 2x. 2. Oh, well, that's reassuring at least. We don't have another loop of L'Hopital's coming. Okay, plug in the 0. Negative cosine of 0. Cosine of 0 is 1, so negative 1 over 2. So we end up, and I guess, well, I probably should have written that as negative cosine of 0 over 2, there we go, negative 1/2. Okay. Got it? So it's not too bad, even if you have to do L'Hopital's a second time. And keep in mind, the nice part about this is it's the derivative of the top, derivative of the bottom. We're not actually using quotient rule, are we? So that makes it easier. Okay, example 3. Evaluate the limit as x approaches 0 of x cubed minus 4x over x squared minus 2x. Thoughts?
Well, we gotta make sure it's indeterminate.
Okay. Is this indeterminate? 0 cubed minus 4 times 0 over 0 squared minus 2 times 0. Okay, so you ready to try L'Hopital's then? So the limit as x approaches 0 of, you're going to do the derivative of x cubed minus 4x over the derivative of x squared minus 2x. Still going to be doing the limit as x approaches 0. What's the derivative of the numerator?
3x squared.
Okay. 3x squared minus 4. What's the derivative of the denominator?
2x.
2x minus 2.
So if the numerator or the denominator was ever, like instead of the minus, if it was multiplication, would we just have to product rule it?
Yeah. I'm trying to think if we see that, and you might. Usually they're a little more basic than that, but you could possibly see that, yeah. Okay, plug in your 0. 3 times 0 squared minus 4 over 2 times 0 minus 2. Where are we at? Negative 4 over negative 2, which equals 2.
I was expecting something shifty with that one.
Yeah, so was I.
Okay. What if I say we didn't have to use L'Hopital's rule on this one?
There it is. Well,
What if I say you could have done this one before today?
Feeling factoring, right?
yeah,
Yeah. So let's go back.
you could factor out x minus 2x, right?
Let's go back, and I need to show it to you. I need to prove it to you.
The second I saw her do no work for it, I was like, what?
Well, I debated how to handle it, because it varies from year to year. Some people catch right away they can factor, and we never do L'Hopital's. Well, I show that it does the same. And sometimes we don't. No one says anything about the factoring. So, let's see. GCF. What's the GCF on top?
X minus 2x. Or no. X
No.
minus x.
GCF on top, there's an x, right? So I'm going to factor out x, and then in parentheses, I'm going to have x squared minus 4. GCF on bottom. X. When I factor out that x, I'm left with x minus 2. Okay, continue factoring. So it's still the limit as x approaches 0. My numerator, I already factored out an x. You're smarties. What do you know about x squared minus 4?
It's x minus 2, x plus 2.
X minus 2, x plus 2, because this is difference of squares. Denominator was already x and x minus 2.
We get x plus 2. We plug in 0 is equal to 2.
So cancel your factors of x and x, cancel your x minus 2 and x minus 2, and you are now doing the limit as x approaches 0 of x plus 2. Plug in your 0, and 0 plus 2 is 2. Did we have to use L'Hopital?
Not necessarily.
No. Now, I will say, depending on what else was asked of you with this problem, the factoring might have been more beneficial. Okay, don't overlook that factoring because that can be key. Because what this would be the graph of, this graph would be a line, y equals x plus 2, with a hole at 0 and a hole at 2. So we could actually graph this now if we needed to. Okay, so there was the shifty part that you guys were looking for. You know, it was too good to be true to just be basic L'Hopital's at that
We
point.
start with an easy one, then there's something that just keeps adding, so we never go backwards.
It never gets easier, huh? Okay, guys, moving on.
We skip steps, that's when you know.
And again, you know, they both work there. Example 4. The limit as x approaches 1 of the natural log of x over 2 minus 2x. Is it 0 over 0? I mean, here's the key you have to remember here. What is the natural log of 1? And it is. Natural log of 1 is 0. 2 minus 2 is 0. That's a good one to know, guys. You don't always have the calculator option to type in your natural log values. I'm as guilty as you guys are sometimes, though, about remembering what they are. So we're going to apply L'Hopital's. The limit as x approaches not 0, 1. We're going to do the derivative of the natural log of x over the derivative of 2 minus 2x. It's still the limit, correct? It's still the limit as x approaches 1. What's the derivative of natural log of x? 1 over x. What's the derivative of 2 minus 2x? Negative 2. Can we plug in? One over negative 2, which is negative 1/2. Sorry, I have something written in my notes off to the side, and I'm not sure why I have it written in there. Oh, okay. I had written into my notes, and I think what I was doing is just showing that this 1 over x divided by negative 2 is the same as saying 1 over negative 2x. Like this fraction within a fraction right here is equivalent to this.
And that's what I did.
Is it?
Yeah, I did 1 over negative 2x and just solved that for 1.
Yeah. And it still works. And if you were to have to apply the L'Hopital's rule again, you would probably actually prefer something in this form as opposed to 1 over x and negative 2. Well, it wouldn't be negative 2 to just apply L'Hopital's, but okay. Not so tricky that time. More just, okay, think about your natural log, some of these basic things here. Okay, example 5. Evaluate the limit as x approaches infinity of cosine x plus 2x over 6x squared.
What are we going to do over?
Well, you can't just do the power thing because cosine x is not a power. The power thing only works when you just have straight polynomials, when it's all just positive powers of x, no other trig functions, log functions, powers thrown in there. So the power thing does not work because of the cosine x. So what happens when we plug the idea of infinity in?
What's that?
Well, since there's x's on both top and bottom, you would just get infinity over infinity, right?
Yeah. I mean, if you plug it in like that, okay, I mean, the part you can see, 2 times infinity is going to be infinity. 6 times infinity squared is going to be infinity. So yes, you're at infinity over infinity, unless cosine infinity somehow takes away from that. Now, think about cosine for me. What's a cosine graph do?
Starts here, valleys down, and goes back up.
Mountain valley, mountain valley, mountain valley, mountain valley, mountain valley, over and over and over. Okay, so keep in mind, as you go on, cosine graph goes up, down, up, down, up, down. So as you're going on and on and on, what values is that cosine graph oscillating between? Right? Cosine will be as low as -1, as high as 1. So this cosine of infinity, its value is somewhere between -1 and 1. When you add that to infinity, though, it's still going to be infinity. Okay, important thought, because we have to have that thought for this upcoming step. Okay, guys, infinity over infinity, that does allow us to apply L'Hopital's rule. The limit as x approaches infinity. And we're going to do the derivative of cosine x plus 2x over the derivative of 6x squared. Don't forget, it's still the limit. So the limit as x approaches infinity. What's the derivative of cosine x? Negative sine x plus the derivative of 2x, 2, over the derivative of 6x squared, 12x. Okay. So let's see. Want to start with the denominator? 12 times infinity. Well, 12 times infinity is going to be infinity, yes? Now, we've got the negative sign of infinity plus 2. That's an interesting thought for you, right? That looks weird. So, sine. What's sine do?
Starts at 0 and goes.
Mountain valley, mountain valley, mountain valley, over and over and over, right? So what does sine, and the negative of that just means it's reflected. valley, mountain, valley, mountain, valley, mountain. Okay. What values does that oscillate between?
Still one.
So it oscillates between -1 to 1. Actually, it's not where I want to write that. Okay, it's oscillating there. So it's going between -1 to 1, and then adding a 2 onto it. That's, and it's not that you even have to write this all down, but I'm trying to help you visualize it. So on top, if it's oscillating between -1 and 1, and then you add 2 to that, it really ends up oscillating between 1 and 3. And so some value between 1 and 3 divided by an ever increasingly larger number.
Zero.
Some very small number or some stationary number divided by infinity is represented as 0. Okay.
Good job, team.
You have 3 to switch out. 3, 4, and 5 are from 77, so you're going to replace them with 12, 13, and 14 from 77.